thanks for having me. I'm kind of excited to be here. As you can see, I teach at LCU down the street, and I know Brock, but no one else in the room. I teach math. Anyone else here in the math program? Brock? Okay, great. Well, we'll start with some vector integrals, and we won't. The math's actually pretty straightforward. But we're going to talk about tools. So I've developed some tools, and also at the end we'll talk a little bit about a project that I did with iPads and other sorts of technology. And my hope is that something you hear today, you can say, okay, maybe that's related to the things that I think about and things that I do. Okay, so to begin, I want to think a little bit about education and learning. So I'm going to get a little nerdy at the beginning, but I hope that that's okay. We'll talk a little bit about just kind of how we think about learning, how we think about different learning theories and such. So there's kind of this debate, and especially if you kind of get into philosophy and stuff, about where kind of is the knowledge at, right? Is knowledge kind of external? Is it out there, and we're trying to grab it and find it and uncover it? Or is knowledge internal? Is it something? Is it like all within your head, and it's only what you see, only what you think internally? Well, I could ask this question, but it would be a trick question, because the way I think about knowledge is neither. I think about knowledge more as the interactions between the two. So when I think of knowledge, I think of it as, yes, we have an external world, but yes, we also have an internal reality. And what's important is how we interact with the external world, and how that external world then influences our internal reality. And that's kind of the development or creation of knowledge. And so, oh, hey, look, it moved. That was exciting. So the phrase that I'm going to use is equilibration, which I will probably only say once because I have trouble pronouncing it. It seems like there should be another I in there somewhere, but there's not. So equilibration, which is kind of this process of harmonizing the way we think about the external world with our internal views. And if you're familiar with constructivism, this is kind of the basic view of constructivism. And it's that we have this external world, and sometimes in the external world you come in contact with new things. And when you come into contact with the new thing, there's really two kind of processes that you might go through. First, you might assimilate the new experience, and that is you have current models of how the world around you works, and this new thing comes in and you say, oh, that fits this current model that I have, and you incorporate it into the new model, and now you have a model that's a little bit richer and a little bit broader than what you had before. It might also be that the new thing comes in and you check it against your internal models, and there's some conflict, and you realize, uh-oh, this doesn't match up with the way I view things. And if that's the case, then you might have to go through accommodation, and that is you might have to reshape or change your internal world, your internal viewpoint. I guess humans aren't near as good at accommodation, probably, but let's not get ourselves too sidetracked with things like that. One example that I thought of was different themes of different schemes for even and odd, for the numbers even and odd. So two ways that you might do this. Let's start with the second one. You might group things, and so you might, if you have a number, and I did this with my daughters, you might have some amount, say, is it even or is it odd? And you might take all of your objects and group them into two collections, and if there are any left over, then if there's one left over, then it's odd. If there's nothing left over, it's even. And I remember going through this with my 4-year-old. She's now 10, but when she was 4, and she could do this, and I was really excited. I was like, yeah, you understand even and odd. And then she went to a preschool class, and they taught her the pat-clap method for doing even and odds, which is where you pat and you go 1, 2, 1, and they said if it's a pat, then it's odd, and if it's a clap, then it's even. And I just screamed. I was like, no, she understands it so much better than that. And but she loved the pat-clap method, and so she adopted the one that I didn't like as much, which bothered me. But okay. But that kind of follows this first idea that even and odds are every other number. So you count, and every second number is an even, and then every number after that is an odd. And that's also valid, right? These are both valid definitions of what even and odd mean. But if, for example, you move into some more abstract things, if, say, for example, you want to start talking about remainders when you divide by numbers, you want to move into things like modular arithmetic when you move into abstract mathematics. It turns out that one sort of scheme is going to allow you for really good assimilation. So if you're thinking in terms of this grouping, you're saying grouping and I have something left over, then all of a sudden if someone says, let's divide by 3 and find the remainder, that kind of starts to make sense. Now you're just kind of broadening that grouping scheme a little bit richer. But if you're doing the Pat-Clapp method, then you might have to go through some accommodation. You might have to reshape and reframe your thinking before you can do things like that. Okay, I don't know if that's helpful. I like that story. We'll talk. Okay, so as I think about learning, I kind of think of it in terms of these words that are kind of Piaget's words of empirical and reflective abstraction. Empirical abstraction is kind of the type of abstract thought we have, the mental models we have by engaging with physical things. So you might say, models of length or models of amount or things like that, or things that are very physically based, right? We're actually engaged with touching and involving things. But as we think about those mental models and reflect upon them, then those abstractions themselves start to have relationships and coordinations between each other. And so we start to coordinate the abstractions, and that's what we start calling reflective abstractions. So reflective abstraction, you have different levels like generalization, which is similar to the assimilation we did earlier. You have some sort of abstraction, you develop some new things, and the abstraction becomes a little bit larger to encompass more examples. You have coordination, which is where you have a couple different schemes and all of a sudden they start being related to each other. You say, oh, I have this one scheme for counting over here, and I have this other scheme for, I should have thought about this before, for something else over here, and these two schemes are closely related, and I could use them together to solve my problem. So you coordinated two schemes. Finally, encapsulation is the one that I find the most interesting. It's whenever you're able to take a scheme and kind of view it as kind of an object to be used in a higher level scheme. The one that makes the most sense for me is number, right? Because we all know what numbers are. My 4-year-old knows what numbers are, but he thinks about them a little bit differently than I do, right? So he's getting past this point, but it wasn't too long ago that if you asked him something like, what is the number 5? Then the answer you get is basically 1, 2, 3, 4, 5, right? It's what you get when you're counting. And so you notice it's very experience-based. We have this action-based, and so it's getting to 5. But of course what happens is after you've counted to 5 enough times, and I think we probably all have, you no longer have to count to 5 anymore for 5 to have meaning. And then what happens is once you don't have to count it anymore, you can start using it in more productive ways. So you could say things like, okay, we can talk about ratio of 5 and 7, and we don't have to count the 5, and we don't have to count the 7. We can think about developing kind of more complex mathematics. And then once you develop a scheme for thinking about ratio, you can say, okay, now we have fraction, and we're going to use that in more complex mathematics. And so this encapsulation is kind of a real powerful tool towards moving to more and more abstract levels of mathematics. What happens with our students, though, tends to be what we call pseudo-empirical abstraction. And here's a fun problem. Brock will know what the answer the students want this to be is. Does everybody else know what the answer should be? Sine of x over x is?
Sin.
Yeah, it's sin, right? It's just sin.
Yeah.
So this you just cancel the x's out, right? And I have witnessed many students do this. Brock, I'm guessing, yeah, he shakes his head. So this is not an atypical thing, right? So the question is, what's going on when the student does this? Is the student just dumb, or or what? And the answer is, I don't believe so. I believe students act rationally. I believe students, against all evidence, I believe they act rationally and perform in ways that are reasonable to them when they create responses. But I think what's happened is we have this abstracting and encapsulating and abstracting, and it's all based back kind of on these empirical results. It's all based on some sort of real kind of tangible, experiential thing. But what happens if that chain gets broken? What happens if all of a sudden they find themselves in a classroom and they're in, they're in Calc 1 or something, and their teacher asks them to think about sine of x over x, and man, they don't have any sort of basis for what to build sine of x off of. They don't have any basis for what to build even this fraction out of. What they're liable to do is they're liable to go back to what we might call empirical abstraction, and that is deal with the objects in front of them, but the objects are the symbols. So now instead of the symbols meaning and representing kind of more complex things, the symbols are now representing just symbols. And so, yes?
Can I ask you a question?
Oh, sure.
So if I were to see that, would there be an assumption that I previously encapsulated the notion of sine x as an entity as opposed to sine times x or something like that?
Yeah, so I think that you would need to. Yeah, I mean, I think you would need to have made meaningful sense out of this, right? Yeah, this is wrong, by the way, right? I guess we could define sine to be a quantity in
right,
like sine
variables, then yes, is absolutely correct.
Unless you put a parenthesis around it,
Right.
to indicate that it is a functional notation.
Yeah.
Then I mean,
But even with parentheses around it, you could still be identifying multiplication. But the thing is when we write this, and we'll talk about this, what we write and what we mean are signs, and these signs are socially negotiated. And I think that we all have reached a point of social agreement that when we write sine of x, we're referring to the function that comes from trigonometry, right? So if a student is unaware of that negotiated meaning, then you're right, they might do something different. And it's not like they're wrong or dumb, it's just that's the thing you might have done. Okay, so my point was that you act on the symbols instead of acting on what the symbols represent, and then instead of cancellation being something like, well, we divide these terms and they divide to make the number 1, and the number 1 of course multiplies to not change the result. You cancel turns into like, well, I have the same thing on the top and the bottom and they like explode or something, you know. And so this is quite frequently occurs. Okay. Okay. So here's my thoughts. So I say this just to move from my thoughts of what I think learning is, and I think learning is inherently experiential. Here's a quote that I found that I liked. I think he actually said it, although it's always a little dangerous when you find quotes. The person who I found who wrote it in their paper, like, worked with Piaget, like was one of his students, or I can't remember if it's a student or he worked, so I feel like it's probably legit, but even if it's not legit, I like the quote, right? Okay, it says, children have real understanding only of that which they invent themselves. And I kind of think this is true of teaching. And that's kind of my point of all this, that in order to get to a point of understanding, you have to build up, and that building involves you personally inventing and creating the mathematics by having meaningful experiences with the external world. And so for us in the sciences, most often these experiences that we want them to build off are physical. Now they don't have to be; they could be other things. 3 examples in mathematics: we like to have manipulatives, and that's these little things in front that we'll talk about for a little while. But I assume that many of you in the sciences do lab assignments, and my guess is that it's for this exact reason, although I don't want to reach out too far because I've never actually taught a class that's not mathematics. But my guess is that it's part of the same reason. You're going, we want students to have meaningful experiences so that those experiences they can kind of invent for themselves the concepts, and they can see for themselves the things that we're learning in class. Finally, I've threw virtual worlds on here because this is really common, especially in the world of mathematics, is we create worlds virtually that students can interact with. And I don't think students have any problem viewing that as something meaningful to relate to. One real common one in mathematics is the geometer sketchpad. And the geometer sketchpad is where you have different geometric shapes and you can click and stretch and say, make this line tangent to this curve and things like that, and get all sorts of really interesting results. And the students can interact with that and engage with that and develop all sorts of neat geometry results from it. But so I think the important consideration, right, and so this is really what I want us to think. So I say all this to say that even though most of you will not teach multivariable calculus, my guess is most of you will have things in your courses that you want to be experiential. And so if you get anything useful out of today, maybe it's just, okay, what sort of questions can I ask myself as I'm developing experiential experiences. I didn't want to say the word twice. But it's funny, as I'm developing experiences for my students, what sort of questions can I ask myself? And the first one is just this. Are the experiences designed in a way that allows the students to reinvent the ideas of the course? I wrote the what is pi here because I had a good, I have a story I wanted to share with, I don't know if it's a good one or not, but it's a story. And it was just about me teaching a class of future elementary and middle school teachers. And they were really good students, and they were hard workers and successful in their class. But we were talking about some different quantities, and we were talking about pi, and talking about some geometry things. And one of the students just raised her hand and she said, "What is pi?" You know? She goes, "I was always told that, I know it's 3.14, but, and I know we use it in the formula, but what is it? Like, who came up with this crazy thing?" Kind of thought. And to be honest, that's a pretty reasonable response, I think, for a student, especially if the student hasn't had experiences that have allowed them to reinvent that. So, and it turned out a couple of the other students in the class were kind of like, yeah, I'm not really sure either. So the next day of class, I brought a bunch of things that are circular, I think a few like cups or bottles and plates, and just a bunch of circular stuff, and just sat them down. And then we got string, and we measured the diameter and marked it, and then we said, well, how many lengths of that string go around the edge? And we noticed that every single object, that marked diameter would go around 3 times plus a little bit. And so as we got going through it, the students were like, oh, so that's why that 3.14 shows up, because it's that relationship. And what you see is that I'm sure she's been told this before. I'm sure she's had class. I mean, I don't believe that her high school teacher never told her what pi meant. But it's the idea, it's the chance that allows the student themselves to say, oh, that number should be 3.14, and that number should be the number that's describing the relationship between perimeter and circumference and diameter in an equal way. Okay, and I tried to think of a good non-example. I didn't want to share any of those. I have them. Okay, so we'll move now to the part where we get to talk about these fun little plastic surfaces. I do all this just to get us thinking a little bit about learning and about experience, about how our experiences are developed. I've been part of a project we call ourselves Raising Calculus to the Surface, where we develop these things and they're for use in multivariable calculus. So what's the idea? The idea is that for most students in multivariable calculus, it's the first real time they've encountered functions of more than one variable. Maybe somewhere they had like an extra class period about it, but for the most part, they're not super familiar with functions of one variable. And then you're stuck with this problem of trying to draw functions of one variable. So I mean, can you imagine trying to draw this? I mean, I would have no success, right? It would just look completely awful. Some of these I could maybe do a little bit better, but even then, it would not go really well. And the students are kind of in the same boat. And so the question is, how can I want them to have experiences with these functions, the same as they have experiences with graphs and such in Calculus 1, but how do we somehow make those experiences meaningful for the student? And there are different options. Well, one option is just, well, let's just go with only two-dimensional things, and that's an option. Another option is to use software, which I'm actually a big fan of. So if anybody's looking for software I know, just look up Paul Seeberger. He has a great online source that just does all sorts of three-dimensional graphing stuff. So, but what we decided to do, of course, as you can tell by the surfaces, was we decided that let's actually engage meaningfully with three-dimensional surfaces. And so that became our project. We have 6 different surfaces. This was an earlier iteration before they became clear. But you see we had 6 different surfaces. We liked them being transparent. It was originally made for cost reasons, because it was cheaper to just get some plastic and mold it. But we actually decided we really like it because you can see through, and so you have a domain, and you can look on top of the domain and see what's going on underneath. You can write on them and erase. It's dry erase, which is really nice. We also have a few other tools. We have planes, and so you'll see some of the students use this later in the semester. It's just a square, right? But we can think of it as a plane, a tangent plane on here and stuff to use for different reasons. We have a tool that we're not going to use today because we're not going to actually calculate derivatives, although I'm sure you all would love it. We have a tool that we call an inclinometer, and I'd never heard this word before. But apparently, the guy from our group who created it found, he said that it's used in like some sort of drafting, or I don't know, someone actually uses these things. But the inclinometer, basically, well, have you heard it before?
Yeah, machinists use it.
Machinists, okay. I guess I'm not familiar enough with doing things with my hands. That's why I'm in math, right? I started out in engineering, and then I discovered I wasn't good at making things, and this became a concern. In retrospect, maybe I should have just kept making things, but I'm very happy with it. But basically, so it's a stick, it has a little bubble, has a little level on it, and so you can hold it on here, and we can make sure this bubble is level, and then when it's level, you have some sort of idea of what this slope is here. And then you can go take that and measure it in whatever way. Because once it's level, you know that this is horizontal, so you can measure the slope with respect to the horizontal. So it's a really nice tool that the students have to develop, and they have to work hard to develop that way of thinking about it. And finally, we have some contour diagrams, which I didn't bring with us, but we basically have, you can see, we basically have a mat that didn't show up on our picture. It's a mat that has all the curves that go along with it, so you can see the representation of these as a curve. And that's actually what we're going to be working on. So we're going to work on contours ourselves. And so for just a little bit, let me tell you what also we think about. So having, as I said earlier, having the object is nice, but what's really useful is how an object is used. That is, how are students engaging in this object in a meaningful way. So we did a few things. First, we wrote a series of exercises that are all intended to be introductory. And introductory in the sense that if we're talking about partial derivatives that day, we're not going to just give them a lecture on partial derivatives, because what they would then do is they would say, oh, I learned this in lecture. And then the experiences, it kind of steals some of the experience from them. We let them reinvent the idea during the experience and say, okay, let's engage with calculating rates of change, and then afterwards, kind of at the end here, mathematize those experiences. So we say, okay, this activity that you just went through of picking a direction, picking a rise and a run, and finding the ratio of it, that's what we'll call a partial derivative, and here's the symbol that we'll use, and here's how we'll calculate that with formulas and things like that. So I refer to that as mathematizing. We always put our students in groups. We have them work together. We value group collaboration. We often emphasize measurement, because you don't want to just say things like it's curvy, right? You want to say things, about you want to be able to attach numbers to it. You want to be able to measure things and have quantities attached to it. One thing that we do, you won't get to see any of this today, because we're not going to do the actual activities that we go through, because they take a while. But one thing that we do is we do have real world contexts attached to our stories. Like, for example, this surface might represent, the height might represent the amount of lead in the ground or something, or it might represent something else. So we rewrite our stories in context. So we don't really want our students graduating our class and then having someone say, what'd you learn in Calculus 3? And they say Calculus 3 is the study of little plastic surfaces, right? And that would not be a meaningful experience, right? We want the little plastic surfaces to represent something more rich. And in that sense, what we really think of is we think of the surface as transitional. And transitional meaning we don't want them to need the surface forever, but we want them to experience it, engage in the idea, and then transition so that they have those experiences to recall, but then they can work on paper, or they can work in a computerized environment or something, and still make progress. We have a whole bunch of topics. So there you go. I want you all to try an activity. So those of you who aren't at a seat, you can come join one of these groups. Congratulations. So I'm going to give you all just a few minutes. Try the activity. I have it printed out on pieces of paper in case your eyes are not great, or just my colors aren't great. So work on it. Oh, and I realized I made a mistake. I made a mistake by not bringing my rulers with me. Because questions 2 and 3, I asked for a ½ inch. Just good luck with that. You can use like some constant measurement that you have. It doesn't matter. Here's another one. Here's a second one to you all. Okay, so good luck.
Well, don't do this.
I think everybody's been successful. Is that right? Okay, well, that was fun. What were the relationships that we observed? Okay, none. Good. No, I know you all did. So who wants to tell me, were there any connections between the lines themselves? Okay, so what's orthogonal? The right angle. So well, yeah. Well, what two things are orthogonal? The curve that you drew that had all the curves on it, and the vector that you drew in the steepest direction that we call the gradient vector. Well, it's a gradient vector with a z component. it's pointing in the direction of the gradient vector. So yeah, and one other thing that students will notice, and we try to push them to notice, is how closely spaced the three lines that you drew are. And we notice that in areas of steepness, the three lines tend to be fairly closely spaced, and in areas where it's less steep, the lines tend to be further out. And this helps them, read a contour map. And so we have a contour maps that we give them, and hopefully, after going through this experience, they kind of start to see, okay, so that's what the contour is. So when I see this line on the contour map, what it was that line that I drew on my surface of all the heights that are the same height. And so we kind of start transitioning them from drawing on the surface to viewing contour maps, and then viewing them in different contexts and say, okay, well, this is the collection of all the points that have the same value, whatever value that represents. So okay, I hope you found that somewhat interesting. I'm going to talk a little bit about how I think about using instruments like this in general. And we have a framework that we like called instrumental genesis, and it talks about the process by which a learner adopts the use of an object. So this object kind of I am able to use it as an instrument. If I gave it to my 4-year-old, he would probably just get a car and race it around on it, right? But it's the same object. But to me, it has different meaning, right? It has. I see things and I have experiences and meanings built in with this object that my 4-year-old doesn't. And so for me, it's an instrument of doing mathematics, and for him, it's an instrument of playing with his cars. Not that that's bad. It's actually fantastic for a 4-year-old. You want to play with cars. So here are some definitions that we have. The object itself is called an artifact. So it'd be the same artifact no matter who's using it. But once you have an artifact, you develop schemes, utilization schemes. That's ways of interacting with the artifact. And those ways of interacting are kind of meant to be accomplishing some goal, or representing something meaningful. And so when I say the word instrument, I don't mean the surface. I mean the surface and all the ways that we have developed of interacting with the surface. So we developed all these different schemes. Now, there are two ways. So I have this picture that we think about interacting with the surface as an external object. And there are two things that happen. One is we call it instrumentalization. And instrumentalization, I didn't choose these names, by the way. These were done by a research group in Europe. But we like their work. They did it mostly with things like handheld calculators and stuff, but we kind of adopted their language into our project. But instrumentalization is where you kind of take the things you know and the things you're thinking about, and you use that to develop schemes for working with your surface. And so the development of schemes is instrumentalization, and instrumentation without the Z is when you're working with the surface, then comes back and shapes the way you're thinking about the mathematics. And so what we see is we have that same process going on, or interacting with the outside world. And so you can kind of think of it as instrumentalization shapes the way you think about the object. Instrumentation is when those experiences then in turn shape the way you think about the mathematics or whatever kind of model it is that you're building. I'll give you a couple examples of instrumentation instrumentalization. The first one, I have a couple students working on these. The students are asked, if you have a tangent plane, on the surface, is the derivative on the tangent plane the same as the derivative on the surface? So the students are kind of asked that question. And then they're asked other things like, is the second derivative the same? And so they're asked a series of questions. So that's the question that they're working on as they talk here. Let's see. I'm going to have to figure out how to make this actually play.
Put it here, right? If we were to just cut this like this, right? So you just cut it right here and you view it sideways, you would see a function with a line at that point. You get what I'm saying?
From your point of view?
No, if you just take it like this and you just cut it like that, right? You just cut it straight through upside.
No.
you cut it straight through, you'll see a function, a curve, and then a tangent line
Okay, I see what
at the
you're
plane, you know what I'm saying? So if we were to take the derivative of that function, you would get a linear line,
Yeah.
right?
Okay, so the students, they say things that are sometimes a little interesting, but what you see is that they are developing schemes. Oh, and by the way, these videos were done in New York City, and I don't know if you can tell the accent of the guy is not West Texas. But really good student, really nice students to work with. And so what you see is that they're developing schemes. So they're saying, okay, we know some stuff about the way derivatives should work. We know something about the way tangent lines should work with curves. And so he's developing schemes. He's developing a scheme of how to place the little plane on the surface. He's developing schemes of how to view it by this hypothetical slicing and kind of ways of thinking about that and relating that to other things. So I call this instrumentalization. And then as we go forward, we'll see instrumentation. We'll see the same group coming back. And they're asked, well, would this be the same at every point, or is it just this one point? And here's what they say in this context.
What are you gonna say?
I guess it's the same. It's the same. I think it's the same now. Yeah.
For X?
Yeah, either the plane or the surface. Because again, this plane is like tangent to the blue that, and even if you use the blue.
So it's same for all of them?
No, I don't know yet for all of them. But I think for F, plotting for X, I think it's the same.
In the X that
Then what, if,
Okay, so I call this instrumentation, and to be honest, the lines are blurred because I think that you're doing both, and you do them quite rapidly, so it's hard to distinguish what one or the other is. But so he's using this object, right, our inclinometer, and he's using it. He previously developed a scheme for using the inclinometer to measure partial derivatives. And so you see this one student M, he picks up the inclinometer and he places it on the plane, and he places it on the surface, and he goes, oh, and him kind of calling up that scheme, that measurement scheme, he realizes, oh, that measurement scheme gives me the same result in both ways. And so the scheme then goes back and goes, that means the derivative should be the same. And then he starts kind of thinking about that and processing why that should be the case. But we see that his schemes are now influencing the way he's thinking and the way he's interacting with the mathematics. Our current line of research is to be able to kind of model and show what types of interactions lead to different understandings. So what I'm, well, kind of at the front end of doing this, but take a whole session of learning and say, okay, here's the type of instrumentalization, the type of instrumentation that occurred to kind of model what types of things might be necessary for these students to learn, about tangent plane approximation or partial derivative or something like that. We won't get into the research, but if you're interested, that's kind of what I'm currently interested in. We're a little slow on time, so but I thought we should probably. What time are we supposed to be done, by the way?
1.
Okay, so not 12:50. Okay, good.
Schedule the one.
Okay, good. That's perfect. Great. Then we have plenty of time. Maybe it's still gonna be a little close. So one thing that's I kind of want to introduce these words of instrumentalization and instrumentation. I'm wondering, just from you all, did you see any forms of instrumentalization, any schemes that you developed when working with the surfaces, and then any sort of instrumentation, ways in which those schemes affected or shaped the way you're thinking? I'm going to throw it out to you all, just see if you all have any thoughts on the activity we just performed. Great, yeah, good.
I think I object to the question because I think that there's some very valuable activity going on here, but I wonder if trying to introduce all this terminology creates a kind of almost unnecessary distinction that is clouding some of it in as a result. And so, and maybe it's just because I'm too dumb to understand the difference, but they seem, as you said, the lines of, the planes are clouded, right? And so, I just don't know then, is this adding something superfluous and not fundamental to what is going on in terms of the level?
Well, so I of course think it is valuable.
Tell us why.
But so So I think it's valuable, and maybe I'll move to my next slide, right? And my next slide is, if you're thinking about, right, if we're trying to think about what sort of things do we want in a classroom, what sort of questions do we want to ask? Well, the first question I want to ask is, what ways are the students going to imprint their understanding onto the object, right? So what ways and what sort of schemes are the student going to develop? Are they going to be developing schemes of interacting with this object that are meaningful, that are representative of the types of things we want them to use? Versus are they going to be developing schemes that are, somehow unrelated to the actual concepts I want them to learn? And then vice versa, how are those schemes going to play back and help them understand what use do those schemes have in developing and helping them move forward?
So I'll say something in terms of interaction with the object. One of the things that struck me first was to actually look at it in this direction. And I
Yeah.
said, oh, that looks like kind of like a sine wave, right? So you have the advantage in this case of actually looking at different
Yeah.
planes in broad ways that you wouldn't necessarily have by trying to look at a two-dimensional surface. So I can say, oh, it looks like a sine wave if I'm looking at it like this, and the sine wave is going down in this direction. And that's something that, from the interaction of the object, I wouldn't have otherwise gotten if I just looked at it, as a series of contours.
Yeah.
People may not think about it that way, but it's kind of interesting to me.
Yeah, so for me, I guess the schemes that I would expect a student to come up with were schemes of noticing that the collection of all points creates a line, right? And so there's a scheme of drawing lines, and then there's kind of this slicing. I saw people looking sideways, trying to get horizontal slices and stuff. And so there are ways of interacting with the object that reflects this. I would say that I've seen things that are somewhat ineffective and often using the role of technology. So I've seen things where students will be using computers or calculators to do their work. And what happens is they develop methods of using the calculator or a computer that actually don't represent the mathematics that you want them to learn. They're able to get the answer to pop out, right? They're able to get the right answer and circle it, but the ways in which they're interacting with the object are not ways that represent it. So I would say that the schemes that they develop are not schemes that are helping them shape the way they think about things. I'm not sure I sold you.
No, but what I was going to say, that's perfectly good, and first of all, I'm going to say I'm just a devil's advocate, and I am highly,
No, it's good.
highly in support of active learning and trying to understand, and what you talked about there, the type of schemes and the way the students think about it and all of that.
Right.
It just seemed to me that I still couldn't quite see the difference between the instrumentation and the instrumentalization, and
Yeah.
maybe because I'm not a bench scientist, I'm pure numbers guy or something. And so that's why I just wondered then, is that adding in unnecessary clutter to the thing? It would be only my point.
Here's the way that I look at it, and here's the way that I get meaning from it, because I'm an engineer that's done a lot of field experience. And to me, part of when I look at the instrumentation tells me something.
Because you know the meaning of the word.
No, because because an instrument shows me something.
Okay.
Like a gauge. A gauge is an instrument.
Right.
Okay. So instrumentation, like a gauge, shows me something. But when I've got something that I need to measure, I need to figure out how to measure it, how to apply an instrument to indicate what it's doing. So I've got the instrumentation that is teaching me, showing me something, and the instrumentalization is how do I measure and get meaning from it.
Okay, that's fine. My lack of understanding of these.
But
that's okay.
But that's why I'm saying connected with me, because
Right,
I work
good.
with instruments.
Good.
So from a point of instruments, that's where it's what will the instrument tell me versus how do I
Yeah. Right.
get something out of it.
That's good.
And what I find really rich about this is, you can give a student any kind of an XYZ function and say, take the derivative of this, and they can probably do it.
Right.
I refer to those folks as algorithmic monkeys in my class, right? Because they're just following a set format for getting the derivative.
Right.
But then if you ask them, draw this, or what does this mean, they just sit there because they don't have the ability to convert from just the symbols on the page to a three-dimensional representation. And this is very nice because,
Yeah.
it gives them a real three-dimensional feel for what they're doing.
Yeah. So I guess I may not have sold you that there's a difference. For me, I think you said it. What was your name?
Jim.
Jim. Okay. Thank you for your comment. Jim, I think said it nicely, right? It's whether you are kind of creating new ways of interacting with the object, or whether those interactions are telling you something, right? So whether you're getting something from the objects. And to be honest, we do these quickly, right? And so it's not always. I mean, there's not always ways of distinguishing, but I think as someone who's creating activities and as someone who's watching students, you kind of see the importance of considering what sort of activities are my students going to be engaged in, and how are those activities then informing the students' mathematics or chemistry or whatever field it is.
Well, like you said, I mean, one informs the other, right? Let's say, we use a cooking example. Let's say you have a meat thermometer, right? And you stick a meat thermometer in and you read a certain temperature, right? So you're getting information from the thermometer.
Right.
The result is to tell you to turn the temperature up or down, right?
Right.
So one informs the other, provides
Right.
a sense of
Yeah.
action.
Well, let me just buzz through. I was going to ask if you have good and bad examples of instrument use. We probably do. Okay. I'll just buzz through a little bit. Just the last thing I want to say, and it's just we'll talk a little bit about how learning is inherently social, and that is how we've been talking about this other thing that we encounter, this external world, as being like a plastic surface. But most of the time, probably it's people, right? Most of the time, what's happening is that we're engaging with someone else, or a community of someone else's, and then we're getting feedback on that engagement. And that's most how learning works, and I think there are people who might say that's almost all of how learning works. And that we socially negotiate what these things mean. I have the phrase publication, and as publication is when you give some sort of effort to communicate out to the public, and then the community then does what they will with it, and then say they might use the word, suppose it's a word, they might use the word differently than you do, and then all of a sudden you go, oh, that's interesting, I didn't think of that word in that context, and so you reappropriate that word.
Have you seen this changing over time? The reason I'm asking is because, 30 years ago when I was doing this sort of stuff, we all did it as sort of rugged individuals, and there wasn't much social interaction. And now you see all the time that learning is intrinsically social. And so, is that a generational thing? Is it a...
Well, I mean, I can't say. I mean, I think our students tend to. Well, it's tough, right? They want to be social, but they also don't. They also want to play on their phones. I'm not sure. But I do think if you just think about learning, like I have small children at home, if you think about how do they learn things, they mostly learn stuff by interacting with people, by communicating with people. So they say a word, and then I repeat the word in a different context, and they reappropriate that word into their own model, into their own schemes. And there are lots of ways that we communicate. We communicate with words, we communicate with gestures, we communicate with images or other things. So there are lots of different ways that we publish or we communicate externally. I have these two videos. I was going to show them. They're only like 10 seconds, but we don't need to worry about it. The real thing is, what's the big difference between these two classrooms? Well, what you'll see is this classroom, like, nobody can see what's going on with anyone else's device, right? So this student can because they had to walk around to the other side of the room. But there's but the ability to share and communicate about what's happening on your screen is really muted in this space versus this space where students are able to kind of pick up their devices and show them to each other, pass them around, or point at each other, and things like that. So this brought us to the idea of public versus private spaces and spaces that we work in. So there are private spaces, which are things which are only meant to be used for you, private spaces, and then there are public spaces, which are spaces in which things are meant to be published, and everyone is meant to engage in those. And so the artifacts that we dealt with were all public, right? It was all spaces. If you drew something, everybody saw that, and it was part of the public communication. If you have your phone like this, it's meant to be private. It's meant to be something that you're kind of engaging with independently. And as we think of kind of public versus private spaces, it's a consideration to think of when you're thinking of activities for the students. Because what we found was that we basically just had two rooms, an iPad and a laptop room. But what we found was that iPads were more versatile. They were capable to be used publicly in a lot of ways. And so we have these signs that we want to share, but the students could actually share all of those signs more meaningfully when they had a versatile device like an iPad than when they had a device like a laptop that was hard to communicate. So often you have things on your screen that are hard to communicate to someone else, And so it's worth thinking about it. And I only say that just to say, it's worth considering what are like the social consequences of a decision you make if you have an experiential activity in your class. And that is, are you creating an activity where students can collaborate over it and can discuss kind of meaningful things? Or are you creating an activity where individuals are actually walling each other off and not communicating with each other? Okay, so that's where I'm done. I think we're out of time. Thank you all very much. I've enjoyed being here, and I enjoyed being poked a little bit. It's good for me.
Well, thank you so much. We appreciate you coming by. Thank you so much.
Should we do any questions, or is there anything else to talk about?
So have you done any actual post hoc testing about the extent to which using an object as opposed to imagining the object
Yeah, that was my question too.
actually manifests a difference in terms of not necessarily exam, but in remembrance and or impact and so on and so forth? Because, in the impression
Right.
is that this certainly makes a difference.
Right.
Does it make a difference? I just wondered if you had done any work on that.
So our project, yeah, we kind of have, our data didn't turn out really great, and that's why I don't have it on here, right? So why is that? Well, the first challenge is we don't have really good assessment tools for saying one student has learned multivariable calculus in a deeper way than others. Are there any physicists in here? Okay, so physicists like to use this force concept inventory. And force concept is really popular, and it's kind of a well-accepted tool. It says if you do well in this test, then you have a much deeper understanding of like the ideas of how forces work. I guess I've never actually looked at it. That could be right or wrong, but they have kind of a really good assessment tool. Nothing like that exists for multivariable calculus. So we can say that our students do just as well at calculating as all the other students. We had some conceptual questions that everybody struggled on. And, so it was hard for us to piece out the differences because I think we didn't have really good assessment questions at this time. Does that help?
Yeah,
your
yeah, and
question
I
at
think
all?
it's something that's an important thing to do
Right.
because, window dressing is great.
Yeah, that's right.
If it's
Well, what
a
we
factor or
definitely
not.
can say is we can look at the communication that happens and say, listen, this is the type of communication that occurred in this room. This is the type of communication that occurred in this room. What do you think? And I think most of us in the field would say that's the type of communication we want to see.
You made a fairly broad statement. Learning is social, and I think perhaps education is social. But I could point out to you several examples where learning is defined in such a way that it is explicitly not social.
And I think that's
So-
my point earlier too.
Okay.
So I think you could arguably say that. So and I haven't thought this one through. I was thinking. Sorry, I was really distracted by that comment.
Oh, that's fine.
So I'm thinking about where could maybe there's a point to that, and maybe you could say that one cannot be educated without another person because education is by definition transferring what one knows to another person and vice versa. So I could see that as a valid argument, but
Right. I mean, maybe I wasn't trying to make a grand statement that all learning is social.
Okay.
I think there exist people who might go down that path. I wouldn't make that statement. But I would say that for the average person living in our society, I think most of what we pick up socially, or at least a large portion. I don't know. It's not like I tried to measure this in some way.
Or you could leverage that from learning experience.
Yeah, but I mean, if you think about it, even if you're thinking internal thoughts about an activity, those internal thoughts are probably being guided by words and language that was developed socially.
So you also raise a good point here. The force concept inventory, universally accepted. So what you're doing here sort of strongly begs the question: why doesn't someone try to develop an equivalent math concept inventory to try to get at,
Getting there.
how do we
Yeah,
do that?
that's great. It's because it's a lot of effort. But if you could, that's right. It would be super valuable if you had them. I know there's a project underway in Calc 1 to do a Calc 1 concept inventory, and it's been going for a long time. And then a lot of other people in the field kind of said, yeah, we don't think this is what I want the inventory. So there's kind of this debating over whether it's actually what people want the inventory
But
to
you're
be or
speaking
not.
to the point about valid assessment. So for example, you're using these models, you're teaching them to think three-dimensionally, and then you give
Right.
them an exam where they're just, you know,
Right.
algorithmically calculating derivatives and
Right.
doing things in 2 dimensions, so you're not really assessing what it is that you're trying to accomplish.
So when I do my class, I do involve a lot of deeper assessment. I'll have students write descriptions of things and stuff like that, and just say, in your own words, describe the relationship between the gradient and the contour curves. And students have to kind of write things out that say this.
And do you find that that actually gives you, that they really understand it at a deeper level as a result of interacting?
Well, I haven't taught the class without these in a long time, so it's hard to say. But I mean, and even then, it would just kind of be 30 students versus 30 other students. So it's hard for me to say systematically whether that's a difference. But yeah. Do we need to go? I mean, are we
Yeah,
like?
we're out of time, but if
Okay.
you'd like to stay, if anyone else has any additional questions.
Yeah, I don't have to be anywhere till like 2:40.
So,
I'm
thank you
good.
all so much for coming, and if you're interested in any of the STEM Core affiliate member fellow, application information, that's all on our website, which is just stem.ttu.edu, so I'd love to have you fill that out as well. Thank you so much for coming, we appreciate it.
Oh, thank you.